Today we will learn about the graph and its representations. Let's start. A data structure that consists of a set of nodes, vertices, and a set of edges that relate the nodes to each other. A graph G is defined as follows: G equals V, E. Let's see an example. When x, y is an edge, we say that x is adjacent to y, and y is adjacent to x. 0 is adjacent to 1. 1 is not adjacent to 0.32 is adjacent from 1. Graphs are directed and undirected. Let's see the difference. One undirected edge has no orientation. Directed edge has an orientation. Two undirected graph. All edges are undirected. Directed graph. All edges are directed. A graph in which each edge carries a value. As you can see the below image, different cities have different values. Directed graph. Directed edge I, J, is incident to vertex J, and incident vertex I is adjacent to vertex J, and vertex J is adjacent from vertex I from vertex I. These are some graph terminologies. Adjacent nodes. Two nodes are adjacent if they are connected by an edge. 5 is adjacent to 7 and 7 is adjacent from 5. Now we see what is path in complete graph. Path is a sequence of vertices that connect two nodes in a graph. A simple path is a path in which all vertices, except possibly in the first and last, are different. Complete graph is a graph in which every vertex is directly connected to every other vertex. A cycle is a simple path with the same start and end vertex. The degree of vertex I is the no of edges incident on vertex I. For example, degree of vertex 2 is 2, degree of vertex 5 is 3, degree of vertex 3 is 1. Undirected graphs are connected if there is a path between any two vertices. Directed graphs are strongly connected if there is a path from any one vertex to any other. Directed graphs are weakly connected if there is a path between any two vertices. Ignoring direction, a complete graph has an edge between every pair of vertices. Loops are edges that connect a vertex to itself. Paths are sequences of vertices P0, P1, Pm such that each adjacent pair of vertices are connected by an edge. A simple path is a path in which all vertices, except possibly in the first and last, are different. Whereas multiple edges or two nodes may be connected by greater than one edge, and simple graphs have no loops and no multiple edges. Graph properties are as follows: number of edges. Undirected graph. The no of possible pairs in an n vertex graph is n asterisk n1, since edge u, v is the same as edge v, u. The number of edges in an undirected graph is n asterisk n1, 2. Number of edges. Directed graph. The no of possible pairs in an n vertex graph is n asterisk n1. Since edge u, v is not the same as edge v, u, the number of edges in a directed graph is n asterisk n1. Thus, the number of edges in a directed graph is less than or equal to n asterisk n1. In degree of vertex I is the number of edges incident to I, i.e., the number of incoming edges. For example, in degree of vertex 2 is 1 and in degree of vertex 8 is 0. Out degree of vertex I is the number of edges incident from I, i.e., the number of outgoing edges. For example, out degree of vertex is 1 and out degree of vertex is 2. Graph representation. For graphs to be computationally useful, they have to be conveniently represented in programs. There are two computer representations of graphs: 1 adjacency matrix representation, 2 adjacency lists representation. Adjacency matrix is a square grid of Boolean values. If the graph contains n vertices, then the grid contains n rows and n columns. For two vertices numbered I and j, the element at row I in column j is true if there is an edge from I to j, otherwise false. You can see in the matrix that there is an edge from 0 to 2, 2 to 1, 2 to 4, and 4 to 3. That's why these are true and else others are false. Almost the same way of finding true and false is seen in previous slide. There is an edge from 1 to 2, 1 to 3, 1 to 4, 2 to 1, 2 to 4, 3 to 1, 3 to 4, 3 to 5, 4 to 1, 4 to 2, 4 to 3, 4 to 5, 5 to 3, 5 to 4. That's why these are 1 and else others are 0. Now we see adjacency lists representation. A graph of n nodes is represented by one-dimensional array L of linked lists, where Li is the linked list containing all the nodes adjacent to node I. The nodes in the list Li are in no particular order. What is graph adjacency list? Adjacency list. For each vertex, the element of each store a list of vertices adjacent to V. Example, as shown in graph, vertex 1 is connected to vertex 2 and 3. Vertex 2 is connected to vertex 3. vertex 3 is not connected to any vertex. Vertex 4 is connected to vertex 3. So, the adjacency of vertex 1 is 2 and 3. The adjacency of vertex 2 is 3. The adjacency of vertex 3 is none. The adjacency of vertex 4 is 3. How much storage is required? The degree of a vertex V equals hash incident edges. Directed graph 7 degree, out degree. For directed graphs, hash of items and adjacency lists is sigma out degree, V equals E. For undirected graphs, hash items and adjacency lists is sigma degree, V equals 2, E. So, adjacency lists take OV plus E storage. It's the same as we have seen before. See the graph as the numbers are mentioned on the vertexes. Now see the chart or box on the right side in which vertices are labeled according to the numbers assigned. Just you to see which vertex is connected to any other vertex. If the vertex connected to any other, then mark 1 or true in the box, otherwise false. As P is connected to R and W, so mark 1 in that box. Same for all other vertices. Q, R, S and T are connected to X, W is connected to S and Y is connected to R and Z, so these all are marked as 1 and all others as 0. In this slide, see part A, which is showing the weighted undirected graph, and part B is showing its adjacency list. Thank you for watching. We will come again with some new topic. Have a good day.